Welcome to this presentation of Limit 2019. My name is Nick Friedl and the topic of this presentation is Weld assessment of solid models using sensor technology. So we will go through all the important steps for the assessment of welds based on continuum element meshes. In the first step, we will import the geometry, then we will define the so-called SW or solid weld sets, which are needed to generate sensors. Then I will show different possibilities and parameters for the sensor generation. I will define welds in terms of weld dimensions and notch cases and code selection. Then we will define some fatigue loads and then we will run a limit job and look at the results. So what does the structure look like? What you see here is a L-shaped corner, which could be a corner of a bogie frame where the longitudinal beam meets a lateral beam with a tubular cross section. So the two or like the four ends of the longitudinal beams could be connected by these cross beams with a circular cross section. The loading situation, we have prepared two load cases actually. So one loading situation would be an in-plane bending, which means that we have a bending moment here at the corner point about the z-axis. In reality, this could happen when we have different tractional forces on the left and right side of the bogie frame. And the second load case involves twisting of the bogie frame, which means one corner moves up and the other one moves downwards. So we get a bending moment in the lateral beam, and here in the longitudinal beam of the bogie frame we would see some torsional loads. And with these two load cases we can define a fatigue scenario and we can run a fatigue analysis. Okay, so let's move to limit and see what the different steps look like. So I will launch limit by double clicking the icon on my desktop, and this is what limit 2019 looks like. Not many changes here compared to 2017. So the first step with a new project is to import the finite element model. In my case, this is a Nastran model, and I'm reading the input deck. Will take a few seconds. Here we are. The color coding actually indicates already different property definitions of the solids. If you want to efficiently generate sensors, it's a good idea to define different properties for each individual component, because then we can easily access each sheet component, which is important during the generation of sensors. So what you see here is the color scheme based on the property sets, and here we can highlight the property sets throughout the assembly. So that's a good way to do it. If you use ANSYS Workbench, usually you have material and property IDs for each component. With other pre-processing tools, you would have to actively generate properties and define sheets with different properties. Okay, so what's the first step if we want to generate sensors. The first step is simply to start the sensor manager. This is what the sensor manager looks like in Limit 2019. So this is a bit different compared to the previous version, and the easiest way is to directly look at the instructions and go through the instruction points. So the first point tells us to create SW sets. And why do we need these SW sets? The idea of joining two parts consists of marking both components and selecting some kind of a topology for the weld. So we have butt welds, we have T-junctions, we have overlaps. And if we simply click on an element, we want Limit to know that all the elements of the flange should be addressed, because we want to generate sensors all around the interface between those two components. So we need an element set where all elements of the upper flange are part of, and this set needs to be an exclusive set so that we uniquely know which set is meant. And since the property information is a unique information, each element has only one property, we can use these property sets to generate what we call the solid weld sets. And this is easy. You first of all have to activate the listing of element sets, and then you simply mark the property sets, and then you say copy to solid weld sets. And what the algorithm does is it simply copies these property sets and adds the prefix SW underline, and Limit will only look in these SW underline sets during the sensor generation procedure. Okay, so this was the first step. We can tick off the show LSET button, and we have finished step 1. Step 2, select a single element on the continuous master. Okay, so the master and slave or continuous and attached sheet idea is the following. For T-junctions and for overlap welds, we have a continuous sheet, and we have a sheet that actually ends at the weld. For T-junctions, this is clear. We have this continuous sheet, and this has to be selected as the first sheet. And then you select a second sheet by simply clicking an element on the rib. Now, doing so, I marked the position where the reference thickness for the sensors will be measured. Okay, so the thickness at this position and the thickness of this position will be the reference thickness for the sensors in the flange or in the attached sheet. Furthermore, by clicking on this upper surface, I also defined the shell normal of the sensor, and it will look upwards. It will always look towards the picked surface, so for the flange upwards, and for the attached sheet it will be pointing to the left side. And one more point, don't select elements near an edge. Always try to select inside, because here the shell normal is unique and clear. Okay, so we have clicked on master element, we have clicked on solid and slave elements, we have step 2 and 3 finished. Step 4 is take a look at the parameters. Here you can define the sensor size. The default size actually supports hotspot stress extraction and nominal stress approaches. This is the sensor length of 2 and a width of 0.5. but you can change these parameters if you like. It is important to define the elastic material behavior, since the sensor section forces and moments are calculated using displacement fields of the finite element analysis, and further on naturally the strain data, and that's why we need material properties defined here, and they have to be equivalent to the parent material properties. I will talk about these detection settings a bit later. So we have finished step 4, and step 5 is press auto creation button, in this case T-junction, so this is the button we need. And limit has generated sensors. If I switch to a transparent view, then the sensors are visible because they are embedded along the mid-surface of each component. So in the standard shaded view, they are not visible. Now in this situation, they are still highlighted. And now, this is a new feature of Limit 2019, I can directly apply my settings or weld qualities, weld types I want to use. So the first step is to select or choose a code, and in my case I would like to use the DVS 1612, which is a railway industry related code for steel structures. And then I can, depending on the topology of my weld, I have different defaults, and in this case I would, or the usual connection would be a double-sided fillet weld with a nominal stress approach. And by clicking on this option, Limit will take the defaults from the library and will apply them to these sensors, and everything looks fine. So with once more apply, we are finished. We have generated sensors, we have applied code specific data, we have defined the dimensions of the throat, and these sensors can be used to calculate the weld between those two components. So that's the simple way to do it. Okay, next. The maximum gap between parts is necessary in areas where we use tight interfaces or contact interfaces. And here in my model, I have a gap which is larger than 25 millimeters simply due to geometric constraints. And if I generate sensors for the tube to the web connection, simply by selecting those two elements and hitting the T-junction, then you can see that here in the lower part where the gap actually opens up to values larger than 0.25 millimeters, we don't really get a nice contour for the sensor generation. So I will delete this once more, and I will increase this value to 1 millimeter, and then we can try again. So I will click the tube. This is the continuous sheet for the T-junction. Then I will select one element here on the web, and I will select a second element on this web. Okay, I missed. So it's very important, if you click in the structure and you don't see an element highlighted on the surface, this usually means that you missed a surface element and some other element in the background was highlighted. So the only way to kind of fix this is to hit the escape button and to delete the complete selection buffer and to start from the beginning, and maybe even show the element edges so you have a better vision of the surfaces. So this element, then this element, and here I will click this side, which means that the sensors for this web will have a shell normal looking outwards, and the same for the right side. So here the shell normal for the sensors will look to the right side. Okay, and now I'm hitting on the T symbol. will generate sensors, and we have here what we need. Nice position covering the 45-degree corner point. Okay, and we want to use a one-sided fillet weld in this case, and then simply hit um, the button with the weld you would like to use, and then we can sweep through the positions to make sure that both sides have the right orientation of the weld symbol. It looks okay on this side as well, and with apply I can finish this operation. Okay, so if I, for example, use these settings for the overlap situation between the tube and the upper flange, this here and this here, again continuous sheet at first and then the attached sheet, and overlap. What does this look like? Doesn't look very good. The sensors in the continuous sheet um, are not positioned in a straight fashion, which means that this maximum gap parameter is not adequate for this type of geometric situation. So I will delete these sensors, and I will set this value to smaller values 0.1 for example, and I will retry to generate, and now it looks fine. Yeah? So even in curved areas and quite difficult geometries, you can use sensors, and usually the generation process works fine. So in this case I want to define the values. It's an overlap, and I will apply data, and with apply I will finish this. So we have these sensors here. Maybe as a last example, a butt weld between those two tubes. Butt weld. Here we are, and then we can apply some kind of an weld settings for the butt weld as well. So this is finished. And now I would like to show you one new feature of Limit 2019, which is the transformations options. We can mirror or copy sensors. So let me first generate some sensors for the combination of flange and web. And this is again a simple T-junction. And I can apply a one-sided fillet weld. Okay. And then I would like to copy these or mirror these elements to the second web. And this is done by simply moving to the transformation option. We have to pick a node that will define the position of the mirroring plane. So in order to do so, I will switch the visibility so we have some edges. I'll pick the node. The orientation of the normal vector to the plane is a unit vector in x direction, which is okay. And I have to select sensors and then mirror. So if I move back to the transparent view, I can see that the selection buffer for the sensors was lost since I have selected a node in between. So I have to reselect the sensors. Okay, I'm not sure which ones they were. Yeah, here. So these sensors here, and by simply clicking on mirror selected sensors, we have sensors on both sides, and Actually, I will undo this because I forgot to tick on move to original sets. I don't want an individual set. I want to have the same weld settings on both sides. So I will mark this again. I will tick this on and I will mirror them once more. And now we have the same sets for the sensors on both sides, and the definition I already stored, like the one-sided fillet weld, is also active for the second side of the sensors, or for the left side. Okay, so I think these are the most important steps for sensor generations, and I would like to move on to the next step, which is the load definition. And to do so, I will open up the load manager. The load manager has 3 sections, and in the first section we define which finite element results we would like to use. In the second section we define linear combinations from finite element results, and in the third section down here we can define load cycle numbers or even define rainflow counting. So this is needed for variable amplitude fatigue analysis, but not for TVS 1612. So we can focus on the 2 upper areas. So at first we have to define finite element results, which means I have to tell limit which finite element results I want to import, in this case from the op2 file. And first of all, I have to define a name. So in this case I will call it load case 3, bending about the z-axis, and the subcase number here is 3. I don't need an increment number. If I skip the increment number, it's the last increment of this subcase. And here I could define explicitly an op2 file, but I will do it on the job level, which is more convenient in many cases. So this was the first finite element result I would like to use, and then a second one called load case 4 underline bending underline y, and this is subcase number 4. Okay, so all we did is to define 2 names internally and to connect them to subcase numbers in the op2. The op2 file itself will be defined later on when we define the job. And now we want to define some combined load cases. We don't exactly know how the twist and the longitudinal displacement interact, so we would like to generate all possible positive and negative superpositions, and to do so, let me show you what this could look like here in a simple text file. We would like to use the bending and in both planes. Here 10% of the bendings and all the plus and minus possibilities within the superposition. So what I'm going to do is I will simply copy this text area, and then I will say create load from text. Then I can simply paste this data here, and that's how we can simply define combined load cases. So how is this to be read? We have a combined load case 1. It belongs to the load group assessment 1. It is defined by a summation of the stresses from LC3 and LC4 using 10% of each. And load case 2 again uses 10% of each, but in one case a negative bending y. And then we have the same thing with a negative bending z, and as a fourth possibility of superposition, both weighing factors minus 10%. That's how we can set up fatigue load cases, and each of these loads, load 1 up to load 4, must be a representative fatigue scenario load case. And limit will go through all these load cases and will search for the largest stress range or amplitude according to what kind of stress measure is needed for a certain code. Okay, so closing this, we can finish the load manager, and we will move up to the jobs, because usually in the setups you would define weld qualities and things like that, weld dimensions, but we have done this already in the sensor manager, so we don't need the setup manager anymore. And the next step is to define a job. In limit you can run the solver in a parallel threading fashion. You can use as many CPUs as are available on your PC, but it only works for shared memory machines, and for CPUs is a good default value. So I will create a job and I will call it sensors TVS 1612. Okay, and now we have to move from the top to the bottom to define different important parameters. So the first one is which preference, which means what kind of finite element code was used to calculate the result file. In my case it's a Nastran, and I want to use the English version, which means that the output variable will be listed in English. Here a new feature of Limit 2019, the standard result file is the H5, which is a format that leads to smaller result files. The old geo format is still available, but it's not default, so you would have to change this to yes if you want to generate an old geo. The geo format is downward compatible with earlier limit versions. Okay, next is we have to define an OP2 file, and then we have to select all our sensors, or actually the setups. Here we can decide if we want to run a fatigue analysis or a static analysis. So this is actually new to limit, new in Limit 2019, that you can define the assessment type in the job manager in a global sense. So what we define here will change the assessments for all active setups. And last is to select the loads and move them to the selected side. And with OK we are fine, and we can run the job. And we can take a look at the command window to see if everything is working out. So this is like an echo of the solver, and since this is a very small model, the analysis is finished. And to take a look at the results, we simply mark this line and hit the view result button. Then the viewer is launched automatically and the results are loaded. We can't see anything because the sensors are embedded in the mid planes. And the first result that would be interesting is the maximum degree of utilization, the overall maximum degree of utilization. And so what we can see is that the maximum degree of utilization is 1.34, So if I switch to a standard legend with values between 0.2 and 1 and everything above 1 magenta, we can see that we have especially the welds between the tube and the web have degrees of utilization that are obviously much too high with 1.34. I can toggle the max value visibility, so 1.34 here at this position. We can look at the degrees of utilization for each assessment point, or we can simply look at the results for loading directions. So for example, in the longitudinal x direction, the degrees of utilization are low, which means longitudinal to the weld. So this is the stresses in the direction parallel to the weld. They lead to small degrees of utilization. Shear is a bit higher, especially here in the area where we have the twist causes shear here in this area. It's 60% degree. It's a 60% usage. And then we have the maximum degree of utilization in transverse direction, and this is here high in this area. Okay, so what can we do? We would move back to limit CIA, and we could directly switch to the setup by simply changing the selection filter to geometry elements, which are the sensors, and simply clicking on an element. Okay, doesn't let me select the element. Okay, so I will move to the setup manager and I will search for this weld. So that's the weld I'm interested in. And I would like to change this type of welding. I would like to change it to a double-sided, no, not a double-sided, but maybe a full penetration weld. So I will import from the library a T-junction HV. It's a full penetration T-weld. And I will get this symbol. If I move it to the other side, it will look like this. And I will apply, close, and we can rerun the analysis just to see if this will solve the problem. Again, we can take a look at the command window. The analysis is finished. And I will import the results once more. And the maximum degree of utilization dropped to 1.08, so we're slightly above permissible values here in the area of the clamping, but this might be an influence of a numerical issue due to the vicinity of the boundary condition. But here in the corner area, that is actually interesting for us. We are pretty much clear and on the safe side. So it would be possible to produce or to design this corner point as we can see it here, not with a one-sided fillet weld, but with a full penetration weld between the tube and the web. Okay, so that's what I was planning to show. Thanks for your attention and have a nice day.